Well, remember, every time you go this way, you subtract 1, right? So if you go this way, you add 1. So it'll be k minus n plus 1. Do you all agree? But isn't that what this is right here? Distribute the negative through. And what do you get? K minus n plus 1. That's that piece right there. You see? So if I cancel this and this and this and this and this and that and that and that all the way down to 1, what am I left with? This expression here over n factorial, which is that side. The looks on your faces. Do y'all have a question or not? You're good? All right, so the big takeaway here is this expression right here is equal to that, and remember that is k choose n, right? That's k choose n. Time to do a series. Now I'm going to give this a title because it actually is an important thing. You hear this in other places. The binomial theorem. Or you might hear expansion. Okay? All right, so that's the overlying title of what I'm about to do. But really, this is all I want. I want to find the Maclaurin series for f of x equals x plus 1 to the kth power, where k is a positive integer. This is a function, right? F of x equals x plus 1 to some power. And I'm telling you that power has to be a positive integer. So x to the, actually, positive integer, I'll say or 0. Or k can be 0 as well. All right? So I'm taking this and I'm raising it to either 0 or 1 or 2 or 3, right? What I want to know is there a way to write the Maclaurin series for this? Right? Is there a way? Now, just so you kind of can wrap your head a little bit about where we're headed with this, if I give you the function f of x equals x plus 1 squared, let's say, then k would be 2, wouldn't it? You don't need a frickin' Maclaurin series for this. You don't need one because you can just, you know what this is, right? X squared plus 2x plus 1. Just expand the binomial, right? Multiply it times itself. So you don't really need a Maclaurin, but I'm asking you for one. So why am I asking you for one? Because what if I give you this? Do you want to expand that? No, right? And if you do, then now do you? You know what I mean? Now do you, right? So is there a way that I can come up with the Maclaurin series, which would be a formula that generates this right here? It would generate this, wouldn't it? That's what the Maclaurin series would do. It would generate this. Can I come up with a formula that would generate it for us without actually having to multiply it out over and over and over? That's the goal. So let's do Maclaurin. So you have your little cheat sheet that I gave you. Are there any extras? Extra one? No? There's one right there. Thank you.
Is this something we're going to be allowed to use on the test?
No, you can't use it on the test, but you can use this to get ready for the test. Okay, so how do we find a Maclaurin series? First, we're given a function, right? We're given a function. Our goal is to express this in some sort of sigma notation, right? Or as just something plus something plus something plus something, written out term by term, right? That's our goal. All right, so the first step, I'm sorry this is so small, but I was trying to make it all fit on one page. The first step is we're going to make a table that's going to be just the derivatives of this, all right? So let's go ahead and start with that. I'm going to erase all this. First step, all the derivatives. All right, the zeroth derivative of this function is just the original function, right? X plus 1 to the k power, right? Here I'm not plugging in k. I'm not telling you what to plug in for k. All right, first derivative. First derivative of this function at x. All right, how do you deal with the derivative of that?
Take the power of k.
Power k comes down, put it out front. Then you have x plus 1 raised to the what power? K minus 1. And then you have to take derivative of what's inside. Derivative of what's inside is 1, so it doesn't matter, right? That's our first derivative. Let's do the second derivative. The second derivative of this is, the k's already here, right? But now that, so it's a constant, it's going to come for the ride. This thing's going to come out. So we have k, then we have k minus 1, and then x plus 1 to what power?
K minus 2.
K minus 2, and then times the derivative of what's inside, which is 1, and so that's all we have, right? Questions? Third derivative. All right, so now the k minus 2 comes out, joins these, k times k minus 1 times k minus 2, and then I have x plus 1 to the k minus 3, right? Let's do one more. What would the fourth derivative of this be? Well, I have the k here, I have k minus 1, I have k minus 2, I have k minus 3, x plus 1 to the k minus 4, right? Yes?
Front, isn't that just k factorial?
Is it k factorial? Is it? Does it go all the way down to 1? It doesn't, does it? Right? It goes k, then k minus 1, k minus 2. In fact, let's keep going here. What would the nth derivative be? Okay, we're going to try and find a formula for the nth derivative right now. And when I'm doing this, let's assume, for the sake of not creating a problem, let's assume that n here is less than k. All right? Let's see what would happen. Can someone tell me? This is the tricky part. This is the part that's hard, right? Look at the n right here. I should probably do the n in a different color. The n right here that we're doing is what the 4 is here, the 3 is here, the 2 is here, the 1 is here, the 0 is here, right? So let's look at, where's the 4 over here? It's right here, right? And this is not quite 4. What is it? It's 1 less than 4. Okay, this is a 3, that's a 3, and this is 1 less than 3, right? This is a 2, that's a 2, and this number right here is 1 less than 2. You see that pattern? So if I follow that pattern, this should be k, k minus 1, k minus 2, k minus 3, dot, 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 to where? K minus n minus 1. I better put that n minus 1 in parentheses. Do you see that where I'm about to go? Do you see where it's coming? Like the binomial thing? Do you see it starting to appear here? Okay, that right there, right? X plus 1 to the k minus n. Good. That's what the nth derivative would look like, wouldn't it? Pretty cool, huh? Now, let's keep going. I know this is almost on the bottom of the board here. I apologize. It's hard to see. Let's go when, I guess this is the hardest part of this, I think, right now is, would this ever become 0? When would we get a 0 out here in front? When would any of these ever be 0? Well, yes, but k is the power here, right? So k I've already given to you, right? I'm saying in terms of what number, what derivative, at what derivative would we actually get a 0 here? Look at your formula. What? So let's try k equals n, all right? So what if I do, I'm going to have to move this one up here. What if I do the kth derivative? Okay, what would happen at the kth derivative? So replace all your, this is our generic formula, right? This is our generic formula right here. Replace n with k and tell me what this is. What is it? K minus 1, k minus 2, all the way till you get down to, all right, replace that k, replace that n with k, right? And what would this become?
K minus 1.
K minus, let me write it down, k minus 1, right? Like that? Which is really k minus k plus 1, which is really 1. So that would come all the way down to 1, right? And then what's this term right here? X plus 1 to the 0. So is that gone? Has that gone completely away? No, this to the 0 is 1, right? That is a number, okay? That is a number. So it didn't go away yet, but on the next one it will. Let's see why. If we go to the k plus 1 derivative, then go into this formula right here and replace all your n's with k plus 1. k minus 1, k minus 2, dot, 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 all the way till you get down to what? Replace, where's our formula? Replace that with k plus 1. What's k plus 1 minus 1? K. K minus k? 0. And we finally get a 0 right here. And then this doesn't matter. This is x plus 1 to the negative 1. But it doesn't matter because this is 0. Do you see that? And so we finally get a 0 in this string of numbers. And so this whole thing is 0. And in fact, if I continue now, that 0 is going to be there the rest of the way, isn't it? It's just going to kill everything off every single time. All right. So let's get back to our sheet. We're trying to do a Maclaurin series. Step 1, make a table of derivatives. And I should tell y'all, this is probably the hardest series that you're going to see in here in terms of finding the Maclaurin series for it. This is probably the hardest one, all right? We created a table, right? We created a table, and we got an expression for the nth derivative. There it is. And now what we want to do, step 2, is we want to take this table and we want to replace all the x's with 0. And we always do 0 because it's a Maclaurin series. And when you do Maclaurin, that's what it is. It's replacing x with 0. So let's take this right here and replace x with 0. And I'm going to follow my thing here. And I'm going to do them in blue to color match what I have here. So I want now, this is step 2, the 0th derivative at 0. So what happens if you plug 0 in for x right here? 1 to the k. 1 to any power is 1. Okay, so that's 1. Okay, now do the first derivative at 0. So now take this formula, replace x with 0. Hey, that's 1 again, right? 1 to the k is, or 1 to any power is 1. So you just get the k that's here. And then you do the second derivative at 0. If you do the second derivative at 0, replace 0 here. Again, you get 1 to any power is 1. So you get k times k minus 1, right? K times k minus 1. Third derivative at 0. Replace this x with 0, that's 1. 1 to any power is 1. So you get those 3. Okay? Do we have enough to see what happens at the nth derivative? Because that's the goal. That bottom right-hand corner, the red, is what we're going for. This is the main thing we want. Can we come up with a formula for the nth derivative of this thing at 0? Well, here's our nth derivative, right? This is our nth derivative. Let's replace x with 0, which is 1 to a power. That's 1. So don't we get this expression right here? Right? That's k minus 1, k minus 2, k minus 3, all the way till we get down to k minus parenthesis n minus 1. That's the formula for the nth derivative of this function at 0. Yes? That's a huge accomplishment that we just got there. So now, what do we do? What do we do once we have that red formula there? Step 3. We do one of these. If it's possible to get a formula, which we did, then we're going to just plug it into the Maclaurin series formula I gave you last class. When we did the sine last class, when we did the sine, I did a table like this and I did the sine function, we could not come up with a formula. We couldn't, because it kept alternating. So what we did is part B of step 3, okay, which I'll try and do another example like that if I have an opportunity. All right, we good? I'm going to write the Maclaurin series now. In general, right, generic Maclaurin series looks like this. All Maclaurin series look like sum n equals 0 to infinity. Then it's the nth derivative at 0, whatever the hell that is, divided by n factorial times x to the n. That is the generic Maclaurin series formula right there. Do y'all recall last class that we actually came up with this right here? We did that. I showed you how Taylor came up with that formula. He kept on taking derivatives, right? Caleb, remember? Okay, so all we have to do now is plug that red piece into here and we have the Maclaurin series. So it would be sum n equals 0 to infinity, right? All right, plug in the red piece, and I'll keep it in red, I guess. No, I don't need it in red. Do you want it in red? Do you care? No? I won't. K minus 1, k minus 2, k minus, in parentheses, n minus 1. All of that over n factorial times x to the nth power. That's our Maclaurin series. But I just spent, before we even started this, right? I just spent a bunch of time trying to convince you of what that was, right? Didn't I show you what that was? There's another way to write that. So this actually becomes sum n equals 0 to infinity. What is it? K factorial over n factorial k minus n factorial, right? That's what's in blue here. I proved that to you already, I think. And then times x to the n. But that can also be written as k choose n x to the n. Right? Because I told you, that's the definition. The definition of this is this, and I convinced you that that's equal to that. The reason I showed you that is because I knew this was going to show up. When I did the Maclaurin, I knew this was going to show up. So I wanted it to easily be able to go to that now. That's it. That is the Maclaurin series for 1 plus x to the n, or x plus 1 to the n. Let's check it, okay? Let's just check. You ready? I would like to know what is x plus 1, let's do to the third power. Now, we could just multiply that out, right? X plus 1 times x plus 1 times x plus 1. If you did that, I'm just going to, spoiler here, I'm going to tell you what the answer is, right? X cubed, anyone know what it is? If you expanded that, anyone know what it would become? X cubed plus 3x squared plus 3x plus 1. Do you believe me? Yeah? Okay. That's what it would become if I expanded that out. Let's show that it's this using the formula we just came up with. So according to what we just determined, this is sum n equals 0 to infinity of what? What's our k? 3. 3, choose n, and then x to the n, right? Let's start writing these out. Okay, let's let n be 0 first. What's 3, choose 0, x to the 0? Well, let's not say what it is, but that's what I get when I plug in 0 for n, right? Then 3, choose 1, x to the first power. Then 3, choose 2, x to the second power. Then 3, choose 3, right, x to the third power. Then what? 3, choose, oh, wait a minute, hold on, x to the fourth, and then wait, 3, choose 5, x to the fifth, and then plus dot, 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 yeah? What can you say about everything from here down? They're all zeros, right? Those are all zeros. Now, we did this already, right? If you have 3 objects inside of a bucket and you want to pick 0 of them, how many ways can you do that? 1. So this is just 1. X to the 0 is 1, right? Plus, now, 3, choose 1. How many ways can you, if you have 3 objects in there, how many ways can you take one of them out? 3 different ways, right? You could pick A, or you could just pick B, or you could just pick C. So there's 3 ways to do that. 3x. Plus, 3, choose 2. That was the example I started with, right? With 3 objects, pick 2 of them out. We did AB, AC, BC. There's 3 ways to do that. 3x squared. And then finally, how many ways can you pick 3 things from 3? There's only one way. There it is. 0's the rest of the way, right? That is the binomial theorem. Binomial comes from the idea that this is 2 terms, right? Binomial. And this is a formula for doing the expansions. So I know if you had me for Cal 1, I showed you all this in Cal 1, and maybe some of you all have seen this, that if you have, let's say, x plus y to the 0th power, x plus y to the first power, x plus y to the second power, x plus y to the third power, that you can write down what these are expanded out and multiplied. Like this first one is just 1. This next one is x plus y. If you square this, you get x squared plus 2xy plus y squared. And then the last one here would be x cubed plus 3x squared y plus 3xy squared plus y cubed. Have you all seen Pascal's triangle before? Yes? No? No? So this can be shown. We could just multiply these all out. The big thing here is these numbers. This is a 1. That's a 1, 1. That's 1, 2, 1. That's 1, 3, 3, 1. The next one would be 1, 4, 6, 4, 1. Pascal's triangle is a triangle where you always have 1s on the edges, and the number in the middle is the sum of the 2 numbers above it. So 1 and 1 became 2. Next one, I have 1s on the edges. This number and this number come from adding those 2 together. That's 3. These 2 together get 3. Next line, add those together to get 4. Those together to get 6. Those together to get 4. That's called Pascal's triangle. And it's used to figure out what the coefficients are for the binomial expansions. If you take a binomial and expand it to a power, you can always get the numbers from Pascal's triangle. The problem with Pascal's triangle is that if let's say I replace the y with 1, okay? 1, 1, 1, 1, okay? So now we're looking at what we just came up with a formula for, right? The problem with Pascal's triangle is that if I wanted to know what x plus 1 to the 73rd power is, I would have to write down all 73 rows of Pascal's triangle to figure out what those numbers are, right? But we can just use this and replace that with 73, and we can get the coefficients with this, right? Do you see these are the coefficients. Coefficient, 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 coefficient. So you can always extract these by, or I guess I could say it this way. See this row right here? This 1 is 3, choose 0. This is 3, choose 1. This is 3, choose 2. And this is 3, choose 3. So if I go to the 75th row, right, my first coefficient would be 73, choose 0. The next coefficient would be 73, choose 1. The next one would be 73, choose 2. And I keep going. And of course I have powers of x next to these also, right? But the idea is we don't have to write the whole triangle out. We just use this. And that we have a formula for. K factorial over n factorial times k minus n factorial. All right. So that's it. That's the binomial theorem. And it comes from the Maclaurin series for that function, f of x equals 1 plus x, or x plus 1. Y'all still alive? You okay? All right, let's do something meaningful now. I mean, not like this wasn't meaningful, but what this was more of like a historical, I'm taking you through the historical development of the binomial theorem. I'm showing you where the binomial theorem comes from. I've erased it. K here, K there. That theorem comes from just a Maclaurin series. That's it. I know when I was a student, oh, here it is. When I was a student, I looked at that, I was like, what the is that? You know, like, where does this come from? You know? It's Maclaurin, that's all it is.
This is still 8.7.
This is still 8.7, yep. We are hunkered down in this section. We will not finish it today. My goal is to wrap 7 up and then talk about chapter 9 next week. And then the final, we can talk about that as well.
How much of chapter 9 do you think we'll get through?
4 sections, but it's going to be like chapter 9 is going to be, here's the basic idea, here are the formulas, let's use them. Chapter 9 is very mechanical. It's almost like I would equate it to when I gave you the formula for finding the area under a curve. Okay? Right? Integral a to b, f of x dx. It's going to be a formula like that, but it's going to be the only thing, we're going to be changing our coordinate system. We're going to be working in polar coordinates instead of Cartesian. So it's not bad. It's not bad. I wouldn't do it if I didn't feel like we could do it all in a day. We can do it in a day. All right, so let's do something meaningful here. Let's try and find the antiderivative of e to the negative x squared dx. So we're going back in time now. We're trying to find the antiderivative of a function. And I'm going to do what most students do, which is go to Symbolab or Photomath, right? And type in e to the negative x squared dx, and just get the answer that way. I've done this in this class before, and it gave us this answer. 1/2 square root of pi erf x. And erf is what we refer to as an error function, which basically what this is telling you is that there is no way that we can do this antiderivative in a closed form. We can't do integration by parts, trig sub. Everything we have, all our tools fail to allow us to find that antiderivative, all right? So what I'm going to do instead is this. I'm going to use the Maclaurin for f of x equals e to the x, which you would now go look at your reference sheet, right? I have that reference sheet, and we have the Maclaurin series for e to the x. E to the x is equal to the sum, n equals 0 to infinity, of 1 over n factorial x to the nth power, which is the same as 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth plus forever. That's exactly what's on your sheet, right? That's what's exactly on your sheet. Yeah? All semester I've watched you just gaze off. You all right? Okay. So that's off the formula sheet, right? So what I'm going to do is I'm going to realize that this formula is a generic formula. I can replace that right there with anything I want, okay? So if I want to replace it with negative x squared, I can. Now also I should point out that when is this power series valid? When can I use this for this? Well, what's the radius of convergence? Or it's everything, right? So this is valid all the time. So I don't have to worry about any domain restrictions at all. I'm allowed to always convert this into this. So I'm going to rewrite this as e to negative x squared, right? I'm going to rewrite that as, I'm going to go ahead and put in the sigma notation, sum n equals 0 to infinity, 1 over n factorial. I'm replacing this x with negative x squared to the n. You'll see that? Just that right there is this, which was that, right? Just plugging it in right there. That equals 1 plus, let's just start plugging them in. I'm replacing all of my x's, right? All of these x's are getting replaced with negative x squareds. So what's my next term? Negative x squared. Okay, I'll just put in parentheses negative x squared. Okay, plus 1 over 2 factorial. Negative x squared, but then that squared, right? That's this one right here. Plus 1 over 3 factorial, and then negative x squared, but then cubed. I'll do one more. Plus 1 over 4 factorial, and then negative x squared to the fourth plus forever. Let's go ahead and square these things and raise these things to powers. This is 1 minus x squared. Is this one going to be plus or minus? Plus, right? Because when I square that, it's a negative, and when I square it, it's going to become positive. So I'm going to write it this way. Plus, what is 2 factorial? 2, right? 2 times 1, that's just 2. So that's 1/2 x to what power? What does this become? 4. My next term, is it going to be positive or negative? Negative, because I'm taking a negative and I'm cubing it. So I know I'm going to have a minus. What is 3 factorial? 3 times 2 times 1 is 6. And then x to what power here? 6 power. Let's do one more. Is it going to be plus or minus? Plus, right? Because that's going to be to the 4th power. So